We'll continue now. Continue. Yeah, Ben? Yeah, Summer?
Yeah.
Okay. So, we're having a look now at Hooke's Law. You write that down? Hooke's Law. Okay, 1 second.
In 4 kilowatt,
Yeah.
Just 90%
Mhm.
is fixed. It
Yeah.
means 4 multiplied by 0.9.
Yeah.
P.
Yeah. So it's 3.6 kilowatts really.
Yeah.
So
My answer with your answer is a little bit different. Maybe it's 20 second or
Oh, it's okay. We can do it next week.
okay.
We can check it next week in a
Yeah.
tutorial.
Okay.
Yeah? Okay. Are you ready, Ben? Huh? We could do it next week, okay?
okay.
Alright. Are you ready? Did you write this down, Hooke's Law? Please, for your help, Lucia. Okay, I need to start. Hooke's Law.
Yeah.
So, you all have seen this before.
Oh yeah.
Yeah.
You pull on it, and what happens as you pull? So, when you pull on this, what do you feel? You feel it wanting to move back,
Yeah.
okay? So the more you pull it, the more force you have, yeah? In fact, Hooke discovered the law here, so it's called Hooke's Law, of course. It says that the force F needed to extend or compress the spring by some distance x is proportional to that distance. That is, F equals minus kx, where k is a constant. And it's like the stiffness of the spring, and x is small. So, we'll get to this in just 1 sec. I just want to draw a picture here. So the idea is, okay. If you pull on this, there'll be a force this way, to the left. And that force is proportional to the x. So maybe in the beginning it's this long, and then you pull it this distance x. The bigger the x, the more force you get. Yeah? Because this is opposite to the x, you know, the x is to the right and the force is to the left, we can say this is F equals minus kx. Now, who can tell me what the units of k would be? What would be the units for k?
Newton per meter.
Correct. Correct. Okay. So the units for the k is Newton per meter. Okay. Now this k is a constant. It's like the stiffness. Like here, the k is kind of small, but for something like, I don't know, like the wood, the k is stronger. That would be, yeah. If it's easy to pull, the k is small. If it's hard to pull, the stiffness, the k, is bigger constant. Yeah, this is called Hooke's Law. So, you'll need to write this down. Proportional then is this symbol.
I know, but I learned before is
It's
similar.
It's similar to percent, yeah. So for example, it means if the x is 10% bigger, then the f is 10% bigger. Yeah. Is this what you mean? No?
No, I mean if I write writing,
Yeah.
essay, IELTS writing,
Yeah, yeah.
I can change percentage and proportion.
You could change percentage and proportion, but not proportional. It's a different meaning. So yeah, you're right. A proportion and a percentage you can change, but not proportional.
It has different.
Yeah.
正反比
No, so we're going to do this. What? You see, because if you speak Chinese, I don't know if what you said to him was right. Maybe you told him the wrong thing. Yeah? So what did you say to him?
That means the one is bigger and the other is bigger.
Yes.
Yeah.
Yeah.
Yeah, that's it. In math we call this 正比.
Called what?
正比.
Zhengbi?
Yeah,
Like,
it means plus
positive.
Negative, negative.
Positive 1 to 1.
Okay. Oh, 1 to 1.
Yeah.
Yeah. It's midnight.
Yeah.
Okay. You wrote all of this down, Khalifa? Yeah.
All this.
I think it's good for your English.
Okay.
Because if you don't know a word, you can look it up and you can learn it.
Yeah. I'm writing.
You know, the English teachers, the two of you make the English teachers very,
My birthday grade EAP is D.
is it?
Yeah.
What's yours?
D.
Okay.
Yeah.
You,
If
yeah,
I get D, I cannot.
I know. How did your mid-semester exams go? When was the exam? 2 weeks ago? How was your EAP exam? Did you do an EAP exam?
Yeah.
Yeah, you did.
Don't know.
Long ago. I don't think it was that long ago. Khalifa, you remember what you got in EAP?
B.
B, yeah. Do you remember what you got in the EAP exam?
AP exam.
Yeah. When was it? Like 2 weeks ago?
But we
It's D.
we
D.
don't have midterm
Yeah.
P exam.
You didn't? You just said you got a B.
Yes, it predicted scores.
No, the exam.
Yeah, the predicted that it was based on the exam.
Yeah, okay. So, did you get the same predicted grade for EAP as your exam?
Yeah.
Yeah. So you got a B in the exam. Okay, yeah. So they must have got D's then in the exam.
Yeah. Today the con
Yeah.
told us.
Yeah. He told you your grades.
What?
He told you your grade.
Yeah.
Yeah, you guys need to work on your English. Okay. What do you think the natural length means?
This.
It's
If
looser.
you-
Give me a sentence.
Yeah, if you don't put do this.
No, you can't write do this in the exam.
Yeah. Without force.
Yeah. Yeah.
The things learns.
Yes.
Yeah.
That's a very bad sentence. Khalifa, do you want to try and give that sentence a...
Natural length means the real length, no adding of any extra natural, just natural.
Yeah,
The specific length of something.
yeah. So don't forget to mention what you mentioned somewhere, which is there's no force.
Yeah.
So the natural length L of a material, you see, now what did you say? You said of a thing. Yeah, of a material is the length at which the material tends to return to. Tends to return to. This means the shape it wants to move back to. So if you pull something and let go, it moves back to the length when there was no force. This is the natural length. Yeah? In other words, like you said somewhere, it is the length before any extending force is applied. So you could say it like this, or you could say it like this. That is, it's the length it wants to be at. So you don't need to write both sentences, you just write one of them. No, forget that. Write both sentences.
Okay.
I'm going to help your English. Yeah? Continue, Ben? Ben?
Yeah.
Okay. Right. Now, again, these two guys, what do you think the word extension of a material means?
I know tension, and E is tension, I think. X.
So what's
X
extension?
means
Result?
Without tension.
Yeah.
Good guess. No.
Okay.
Do you know this word? Now, I know you're looking at this and you're seeing the word tension.
I know
Okay.
EX.
What's EX?
Like my last girlfriend.
True. So this is last girlfriend tension. Is it? Yeah, it's not this. Okay, I don't think you know this word, extension. Extension. Ah, guys. Alright, do you know this word, Khalifa, extension?
Yeah.
What was it then?
Extension of a material means when a particular amount of
Yeah.
something is added to the original length.
Yeah, that's it. It's added to the length. So, an extension of a material is the length at which the material is extended beyond its natural length. So that's what you said. You said, what did you say, additional?
Yeah.
Extended beyond its natural length. So, for example, if this is the natural length, and then you pull it this much, this is the extension. It's the extra length after the natural length. You understand? So, for example, if this is the length and I pull it, then the little extra is called the extension. Okay? That's, in other words, that's the X in the formula.
Yeah.
Okay, if you can write this down now.
question.
Yeah.
If we finish the physical essay,
Yeah.
then we don't have the physics part in Friday.
Correct.
Sorry.
Pardon?
The physics support on Friday
Yeah.
is only for now for the essay.
If you finish your explaining the works, you don't have to come.
No, there's still more to do. Did you get your 800 words?
800.
For Friday, remember?
It's 800 word.
Well,
400 to 800.
yeah, I said if you can have at least 400, that would be really good.
So, no, 3 something. So I'm writing it on the paper and then I'll write it.
Okay. Is this better for you?
Yeah, I want to make sure I don't miss anything out by reading it on the paper. After then, I'll write it on the module.
You got this?
Yeah.
Ben? You got this? Continue? Okay. Now, if you were to make a graph of extension and force, you will get something that looks like this. Now, this is actually, it's not difficult to do. So I don't know if you've seen these before. They're a little machine, like a little, looks like a clock, yeah. And at the top it says 0 newtons. And then when you pull this, it measures the force. So the hand moves around. So maybe it says like it's 5 newtons. You know, it moves around as you pull it. Maybe you've seen these before.
Yeah,
You can use them for the weight. Yeah. So if you were to pull this a distance x and make a graph where you have x and f here, okay, you'll get a straight line like this. What does this graph represent? What does the slope and the area represent? So let's have a look and see. There's x and there's f in newtons and in meters. So you know Hooke said F equals minus kx. Now I don't care about the minus just for the moment. So F equals kx. The minus just tells me it's opposite direction, okay? So if you write F over x, that's equal to k. So it means here that the slope is equal to k. Yeah. Now what about the area? What do you think the area is? Well, let's have a look here. Work, yeah, because this unit is meters, this unit is newtons, so the area would be units of Newton meter, which means the area here is in units of joule. So this area represents the work done to pull it. Okay. Oh no, it's cut off. I can't see it. Hang on, let me fix that. Well, I can just write it here. So, yeah, I need to, maybe I could make that smaller. Okay, anyways, here, if you want to calculate the work, the potential energy, the area is a half the base by the height. But what does F equal? F equals kx. So you get a half k x squared. So when you pull a spring, you do work. But this work equals the energy now in the spring. Because if you let go, what happens to the spring? It moves. So yeah, so it's like you put energy in the spring. Okay? So this formula here is for the energy stored stored in the spring. Do you get the idea here? Okay, so I think you should write this screen down. Yeah? You got
Yeah.
that?
Yeah.
No. Just wait. Continue, Khalifa?
Yes.
Are you sure? Okay. Okay. Now, in real life, this is what actually happens. You can keep pulling it and pulling it and pulling it, but then at some point it breaks, and it's no longer stretchy. So, I give you a picture, okay? Here's the spring. If you pull that, you can get a graph like this, okay? But if you pull it too much, and then you let go, it doesn't snap back to its shape. It's like it's broken. You know, like you pulled it too much, now it doesn't really stretch anymore. So what happens in real life, you have X and you have F. You get a straight line, but then at some point it stops and it starts to curve. So now it's no longer as much force, not as stretchy. So this point here, this is called the elastic limit. Okay? And this part of the graph, from here to here, this is called the elastic region. It means it's elastic. Elastic means stretchy, like this. And does anyone know the opposite of elastic? So what do you call it here? Does anyone know? So what's the opposite of elastic?
Steve.
Good guess, actually, yeah. Good guess. It's a word like this. We call this part plastic region. Okay, so in physics, something like this, you would say is plastic. Okay, because if you change the shape, kind of stays the same. Maybe it moves a little bit. Okay, but something like this is elastic. Okay, that's elastic, whereas this would be plastic. Do you understand the difference in the word? Now, in the exam, they sometimes ask you to draw this graph in the exam. So they want to see elastic region, plastic region, and elastic limit. Yeah?
Find the picture.
Yeah, they want you to draw this sometimes. What? It's good. Easy marks. You drew? Yeah. Yeah?
Yeah.
Okay, so the word elastic means the material follows Hooke's law. So you see here, this is Hooke's law. Plastic, it means, you could probably guess, the material doesn't follow Hooke's law. elastic limit, the point when the material is no longer elastic and becomes plastic.
So how about the lessons?
Say again?
If you move it to the elastic limit and she is broken, but you give some heat and he will move to the beginning. Lessons.
Yeah, that's more complicated. We're keeping it simple. You're right.
Yeah.
There's other things too. We'll actually talk more about maybe stuff like that in the next lesson. Next topic. Yeah. Continue. Yeah. So, a mass M is hung to an elastic material which is suspended from the ceiling, or a mass M sits on top of a spring. In both cases, the situation is the same. A mass at the end obeying Hooke's law. So, this is what I'm saying. You could have a picture like this. So maybe you have this here, okay, and somebody pulls it down a little bit so it starts moving up and down like this, okay, or maybe it's like this, it's on the ground, and there's a mass here, and somebody pushes down on it, goes thick, and it starts to bounce up and down like this, okay, or even it could be on the side like this, maybe on a table, and somebody pulls it to the right and it moves back and forth like this. Yeah? In all these situations, the motion is simple harmonic motion. Do you remember simple harmonic motion? This type of motion? Yeah. There is a formula to calculate the t. And the t is equal to 2 pi root m over k. This is the time. And what's interesting, for me anyways, what's interesting is this formula is the same in each of these pictures.
What? Why? It's every steps we can use the.
Yeah, you can use this in all 3 pictures. Amazing, right?
Yeah. It seems like different.
It seems like it should be different. Now, Summer, here, I understand that the weight is this way.
Yeah.
Here the weight is this way,
Yeah.
and here the weight is this way.
Yeah.
But the weight does not affect the time.
Even if it's much.
The mass affects it because of Newton's F equals ma.
Yeah.
So the reason the m is here is actually because of this formula. But the weight doesn't affect it. It doesn't affect the time.
Yeah.
So the time will still be the same. Now maybe though it has some effect. Like for example here, the amplitude might be bigger because it's hanging. But it doesn't affect the time. So t is 2 pi root m over k.
Mm.
Yeah.
If we put the without these things, yeah, like this,
Yeah?
yeah, we can use
Yeah.
the formula.
Yeah.
Oh, okay, thank you.
It's used really any time there's a spring. It doesn't matter how the spring is. Which is strange. I know, it's strange. I could prove it, but I won't. Because the proof is a little difficult,
Yeah.
and you don't need the proof for the exam.
Okay.
Okay. Right, did you write this down? Yeah? Okay. Now notice that this formula doesn't have the natural length or the amplitude in it. So this is what I was saying to you somewhere. You know, the T doesn't care about many things. It only cares about the K,
And
the M, and that's all it cares about. Okay. Continue? Right. Here's a very simple question. A rubber band has a natural length of 10 centimeters and a K of 1 Newton meter. And then you stretch it to twice its length. So you have a rubber band and you stretch it to twice its length. 20 centimeters now. My question is, what is the force? So use Hooke's law, tell me what the force is.
20.
No.
Oh, 10.
No.
Just
Hello?
oh,
Yeah,
sorry.
No.
0.
0.1.
0.1 newtons.
Yeah.
Because this is centimeters.
Yeah.
You have to convert it
Yeah.
to meters. Yeah? Okay, so that's fine. Right. Now, a spring is hanging from a ceiling. The weight is 2 kilograms and the spring extends by 5 centimeters. What is the K? So I'll draw the picture for you. Yeah? Here's the ceiling. This is hanging from the ceiling. And it extends. So like you can picture it like you have a spring and then you put the weight on it and then it stretches down. Okay? So it extends by 5 centimeters. And this is 2 kilograms. And my question is, what's the K? And of course, I'll remind you that in this picture it is not moving.
The length is 5 centimeters.
Yeah.
3.924.
Okay, so did you say that there's a weight here
Yeah.
of 2G?
Yeah.
That's 19.86 newtons. So that means the force here must also be 19.86 newtons. And Hooke said that's equal to Kx. So I think your answer is too small, Summer. K will be 19.86 over 0.05.
2 is 9.81.
Oh, sorry, so this is 9.82, is it?
19.62.
6.2?
Yeah.
Yes. Sorry. 6.2.
Yeah.
I'm very tired.
Oh, 0. Yeah. My answer is wrong.
You're still wrong, yeah.
Sorry.
What is this, Ben?
300.
Yeah.
To
392.4 newtons per meter.
Yeah.
Okay, fine. Right. A spring with a constant of 2 is attached to a wall. So it's on the wall here. And a boy pulls it 10 centimeters. How much work has he done? So what's the formula here? What formula do you use here?
F over x plus k.
Not this one, no. For work.
2
No?
1 over 2 kx squared.
That's it. 1 over 2 kx squared.
0.00001.
No.
30. 0.000.
No. No. Not 3 zeros. 2 zeros.
Oh, sorry. It's 0. 0.1. Sorry.
Yeah.
Sorry.
And what's the unit?
The
Joules.
joules.
Yeah?
Yeah.
A rubber band is attached to the ceiling. A 100-gram weight is hung on the rubber band and it extends 5 centimetres. The weight is pulled down a further 4 centimetres and released. How long until the weight reaches its maximum height? Okay, I'll do this one. So, well, we'll do it together bit by bit. Okay, so step 1. You have a rubber band here, and then somebody puts a weight on it, and it extends down a distance of 5 centimetres, and it's a 100-gram weight here. Okay?
Yeah.
So my first question for you, give me the K.
No.
Can you get the K again?
Hmm? 19.62.
Okay.
Huh?
Did you have the 5?
Yeah.
Okay. Yeah, Ben, is this right?
It's 100
Grams.
Grams.
So it's 0.1
9
kilograms.
Yeah.
So that's 0.981 newtons. Yeah?
Yeah.
Okay. Now what somebody does is they pull it down another 4 centimetres. So what happens now, because they pulled it down past this level,
Yeah.
they pulled it down to here, it will then go up and down like this. So it'll go 4 centimetres under and 4 centimetres over this line. My question is, what is the time it takes to go from here to here? Is that t? No. It's a half t. Right? Because t would be here, up and down. And I want the time to go from the bottom to the top. So that formula is a half t, which would be pi root m over k. Yeah. So that's pi root 0.1 over 19.62. No, because it's a half t.
But
Half.
A half 2.
okay.
We are tired.
Me too.
.224.
Is that okay? Are you sure? Summer, is it okay?
Yeah.
Khalifa, did you write this down? Yeah? Oh, you didn't write this down, okay. Do you want to write this down?
Yes. Why we don't use the length and the force to calculate the time? We just use the M and K.
Which force?
Yeah.
Ah,
Yeah.
not necessary.
Yeah.
Also, you understand, Summer,
Yeah.
that the 4 is not important.
Yeah, the force. Yeah, I said it's amazing.
Yeah.
Yeah. with all the force and those.
Yeah, yeah, it is amazing. Yeah. Yeah.
So if we want get a t,
Say again.
if we get a t, we have multiply 2.
If you got the t, you would need to divide by 2. Oh, but if you multiply this by 2, that's the time to go up and down.
Yeah.
My question, Ben, was what's the time to go from here to here? That was my question. My question was, how long until the weight reaches its maximum height?
Okay.
So that's only a half t. You look confused, Ben.
Yeah.
You are confused?
No.
Summer, are you confused?
No, I'm confused the exams questions. Our physics exam question.
Okay.
Maybe I know something. Or where I
Maybe
get it
you
wrong.
do know something.
Yeah.
Okay, there's 5 minutes left. And the next time I see you will be Friday for the essay,
Yeah.
but physics class, the next one's on Monday, right?
Yeah.
So that is enough time to finish this lesson and the last lesson. Yeah? So you can start now on Hooke's law, please, for 5 minutes.
I need to sleep.
No, I know that feeling. Okay, try this for 5 minutes. Just 5 minutes, okay?
So,
Yes.
show me what you played instead. Yesterday you said.
I will. I'll.
You forget.
No. Well, no, I did forget, but let me turn this off. I'll get a picture of the game, then I'll show you, okay?
Okay.